Okay, so if we are that housing inspector or lawn inspector that has to go around and make sure everybody's following the rules and regulations, and there is no Euler circuit, there is no way, given the streets or the graph that's present, to travel every edge, every street exactly one time and get back to where she started, where she parked her car or truck. How can we make sure she's doing the least amount of walking possible? Okay, so she can get done in the most efficient amount of time. That's where this process called Eulerizing a graph comes in. Okay, so Eulerization is the process of adding edges to a graph in order to create that Euler circuit that we want on the graph. Okay, so our goal is to create an Euler circuit on that particular graph by adding edges. Okay, so the problem is, remember, to have an Euler circuit, you need vertices all with even degree. Okay, so in order to Eulerize a graph, what we need to do is get rid of the vertices of odd degree. And so we're going to duplicate edges to connect pairs of vertices with an odd degree. When you do that, of course, it results in two vertices with even degree, because when you add a degree, your odd number turns into an even, okay? And as soon as you have a graph where every vertex is even, now you have an Euler circuit, okay? Now, be very, very careful here. We can only duplicate edges. We cannot create edges where ones didn't exist before, okay? Duplicating an edge means we walk down the block and at some point we walk that same street again. Putting in a whole new edge between two places means you're creating a whole new street where one didn't exist before. Okay, we're not going to build a new road. We're just going to walk along the same street more than once. So no putting in edges where edges didn't exist, where there wasn't a connector at some point before. All right, so we're going to take this graph right here and we are going to Eulerize it. So the first step is to find any and all vertices with odd degree. And so you'll notice that those are vertices B and C, okay? Then what we want to do is duplicate any edges that connect those. So B and C are already connected by an edge. So duplicating it, drawing in, and it looks like an additional edge, but remember, it's not putting in a new road. It means we're going to walk that between B and C twice, okay? Now we have a graph where all the vertices have even degree because B and C now have degree 4. That's an Eulerized graph, and there would be an Euler circuit. We could start at any vertex we want and end at that vertex. All right. Looking at the next one, we've got the exact same graph. So you can think of this as a neighborhood, or like the intersections of streets where the vertices are. We want to find 3 different Eulerizations for that graph. So the first thing, again, identify any and all odd vertices. So here in graph 1, well, they're all going to be the same, but I'm going to label them in graph 1. Those are all the vertices of odd degree, okay? So the question is, how can we make an Eulerization of this graph? So how can we connect up edges that or connect up vertices by duplicating edges? So again, no making new ones. We cannot, for example, connect here where I'm putting in a dotted line. There is not a street or an edge that goes directly from one to the other. We cannot do that, okay? That is not allowed. That is against the rules, so we're not going to do that, okay? What we can do is we can go walk that road again twice, or that edge twice, those are among those top 2 vertices. We can do the same thing between those bottom 2. Okay, but notice these 2 sticking out here on the ends on the far left and the far right. There is no edge that connects those 2 directly. So I can't just connect those up. That would be putting in a whole new road. So I'm going to have to go somewhere else. All right, well, notice that this vertex here, I'm going to put a little arrow, it's only connecting to other vertices of even degree. So as soon as I add an edge, duplicate an edge, I'm going to turn one of those vertices into a vertex of odd degree. I don't have the choice, okay? So for right now, I'm going to go ahead and duplicate that one. And then notice we have a problem. Okay, this vertex right here, which I'm going to put a star here, okay, that vertex now has odd degree. We have an issue. Okay, so now I have my starred vertex of odd degree, and I have my vertex over here at the far right of odd degree. There's still no edge that connects those two together. So what I can do is I can take this one at the far right, I connect it here to the middle, and now this guy has odd degree. I turned an even into an odd. And so now the ones I'm dealing with, my stars there, those currently both have odd degree. They have degree 5. So to remedy that situation, I'm going to get my stars out of there just to clean things up a little bit. To remedy that situation, what we can do is then duplicate the edge between those vertices. And now if you start looking at every vertex in this graph, every vertex does have even degree. Even these guys right here that we added all those edges to. They were even before, but notice we added degree 2. We added 2 edges going in, so we went from degree 4 to degree 6. So there is one potential Eulerization. I'm going to get those extras out of the way, declutter our graph a little bit. Okay, so there's one possibility. Now, if we do that again, so we know the same vertices are odd to begin with, we're going to come up with a different Eulerization than the one we just did. Okay, so let's say I can't connect these two in the top row together. That wouldn't be the same. So let's say I connect them. Oh, let's go that way and that way. Okay. If I did that, now those vertices in the top corners, the top left and top right corners, those are now vertices of odd degree. And the ones right below them also have odd degrees. So if I duplicate those edges, now I have vertices of even. All of those that I've already messed with, including the ones in the corners, are even. Then I have these two guys at the bottom. They're currently odd, and I can hook them together, and that's different than my first graph. So there's another Eulerization that's different, okay? You could walk those particular streets where I've got those extra edges. You could walk those twice. All right, let's look at one last one here. Okay. And again, trying not to duplicate what we just did. And I also don't want to create graphs that are equivalent to each other. So I don't just want to draw like the same thing but flipped upside down. We want to create something entirely new. So with these top two vertices up here, these two that I'm talking about, I can't duplicate the edge between them. I've already done that. Okay. I'm not going to go over to the corner vertices. I've already done that. So I want something that's distinctly different. So my choice is going to be to duplicate the edges that are going kind of below them. Okay. If I do that, remember, I just created vertices that were even, the ones in the middle there, now they're odd. I'm gonna have to do something about that. Okay. So if they're odd, and knowing that these ones at the side are odd, I'm gonna hook these up here. Okay. So now those look a little different. And so now I've got evens everywhere except for, again, this last one at the bottom. I could potentially hook those two together. Those would not be isomorph or equivalent graphs. I could also, if you want to get super creative, you can connect up that way, but then these vertices in the middle, those are odd degree, and you'd have to hook them up again. So there's like not a right or a wrong. You can put in lots of edges. Okay, you can do lots, you can do little, but in the end, every vertex has to have even degree. Okay, now there is a reason I chose to do that last graph the way I did, and that leads us into this next question. Which of the Eulerizations is the most efficient? Which is the least efficient? And I intentionally did number 3 the way I did to make it a little less efficient. Efficiency is going to be measured in how many edges you duplicated. Okay, so if you look at this first graph, we duplicated 1, 2, 3, 4, 5 edges. In the second one, we duplicated 1, 2, 3, 4, 5 edges. And then the last one, we duplicated 1, 2, 3, 4, 5, 6, 7 different edges. So the most efficient would be number 1 and number 2, and the least efficient would be number 3. And the decision is based on the number of edges. Okay, so we duplicated the fewest edges. Sorry, my handwriting is not doing well today. We duplicated the fewest edges with number 1 and number 2. So again, if you were that person that was out there walking on a really hot or really cold day, for example, and you want to get done as fast as possible, you should do the duplications shown in 1 or 2, not in 3. That's the day where it's gorgeous and you want to take a little extra time. You don't want to, you want to work out your full day. You don't want to get done 30 minutes before you get off work. You want to take your time. That'd be the one there. Okay. All right, so again, I want you to pause the video and I want you to Eulerize all of the graphs that remain on this page. So go through, find all your vertices, all the vertices of odd degree, start adding edges to make sure whenever you are done that every single vertex has even degree, and then come back and compare yours to mine. And again, mine is not necessarily the only right answer. Yours might work too. The key there is, do all of your vertices have even degree? All right, so let's make some comparisons here. In the first one, all the vertices that are filled in, those are all the vertices of odd degree to begin with. Whenever possible, if you're trying to be most efficient, do connect 2 odd vertices together by duplicating an edge, okay? Do your best to connect an odd to an odd. Turn them into an even right away if you possibly can. But in this case, you do run into, at some point, there are 2 that are not connected already by an edge. So you have to kind of go to an even vertex twice to keep it even and to turn your 2 odd vertices into even. So there's one possibility. In the 3 below, again, I've highlighted the vertices of odd degree. So notice in the case of E and B, those are connected with an edge. And so I can duplicate the edge from E to B. I'm going to go kind of around the long way here to make that happen. And G and A are already connected by an edge. I can duplicate that edge as well. And again, I'm going to go around the long way just to kind of avoid clutter in the graph. It's plenty cluttered as it is. With the next one, B and D are the vertices of odd degree. And notice there is not an edge between them. So there is not an edge to duplicate between them. I'm not going to create a new road. So the most efficient way would be to go to a vertex that maybe they share, that they're both adjacent to. That would be vertex A. So if I duplicated the edge from A to D and from A to B, that makes B and D both have even degree, turning from odd, and then A stays even because I added degree 2 to that edge. And then similarly with this next one, D and F do not have an edge between them. They are not adjacent. So we're going to have to kind of pick a middleman, if you will. There are lots of ways you can do this, but again, most efficient, they both are adjacent to C. They are both adjacent to E. And so the most efficient way will be to duplicate the edges from D to C and C to F, or from D to E and E to F. Again, take your pick. Just in the sake of having plenty of space, I'm going to duplicate the ones connecting to vertex F.